So today with graphing rational functions or radical functions, in this case f of x equals square root of x. Whenever you're dealing with a square root and you try and plug in a negative number into it, like square root of -4, if we tried that on our calculator, we're going to get an error message, and that's because you cannot square root a negative number. So it says...
One thing.
I'm sorry, what's up?
So since you can't square root a negative number, don't you like split it like the square root of -1 times the square root of 4, then you can get like I times I square root of 4, right?
Yeah, you could do that. So you would get like two. You would get 2i, but we're only going to deal with real numbers in this class. We're not going to talk about imaginary numbers this year, so we don't need to worry about that aspect of it, which is nice. But yes, there is a way to deal with imaginary numbers as well, where you can split it into a square root of -1 times 4. So we're not going to worry about that part of it, okay? So in this case, though, we'll just say undefined, undefined, undefined for all of these values. We can't graph any of these points because they're all imaginary points. When we get to these numbers, like we have square root of 0, we get 0. Square root of 1 is 1. And then we'll get some weird decimal answers on some of these. So like when you do square root of 2, you're going to get 1 point, we'll round to the nearest hundredth, we'll say 1.41. And when you do square root of 3, you're going to get 1.73. And then square root of 4 is 2. Okay, so when we're talking about radical functions and domain and range, for these square root functions, domain is going to be positive numbers. So we can't have any negative numbers for the x values. So these -4, 3, 2, 1, those can't be in the domain. That's why the domain starts at 0 here. And it includes 0 because we actually got an output for y as well. And then goes to positive infinity. And then the range, as a result, also positive numbers. Starts at 0 and then goes 1, 1.41, 1.73, 2. So the range goes from 0 to infinity as well. All right. Now, if I were graphing this function, let's see, I could go ahead and put a scale of 1 in both directions here. So let's just do 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So we're just going to do a scale of 1 in both directions here. 1, 2, 3, 4. And plot some points, 0, 0, 1, 1, 2, 1.41, 3, 1.73, 4, 2. When we sketch our curve, it's going to be a smooth curve. We'll put an arrow on it to show that this goes on forever. All right, in that direction. But we can even tell that it starts at the point 0, 0 here. So if we're thinking about domain, it's like all the x values. So as we're going from left to right, we can see the x values start here, and then they go on forever. The range, again, starts at 0, 0, and then we're going up. And even though this is going out to the right faster than it's going up, it's still going up forever. And that's why the range goes from 0 to infinity as well. And so that's how we graph a square root radical function. The downside is we want to have nice integer values to deal with. So we want to work with, the best way to put it is integer outputs. So like this. So we had 4 and 0 and 1. What we don't want is like 2 and 3 here. We would prefer not to have decimal output values. So it'll be easier to graph if we can find integer values for the inputs and integer values for the outputs. So what that means is when we're selecting our table, we want to choose some better numbers here. So for example, we know 0 and 1 worked for x, and then we know 4 worked, it gave us a 2 for the y value. What's another value we could pick? So like for example, when we did 4 for our input, the square root of 4 we know is 2. What's another good value we can put as an input that's going to give us an integer value for an output? 9. Exactly. And the square root of 9 is 3. How did you know 9? How do we know that?
Because it's a perfect square.
Exactly, it's a perfect square. So if we pick perfect square values, we're going to get nice, reasonable integer values output as well. So for example, 9, square root of 9 is 3. Square root of 16 is 4. And then we could do square root of 25. And that's 5. So that'll give us another nice one. And then finally, we'll say square root of 36. Just picking nice, perfect square values. So it's going to change our x-axis a little bit, but we're getting nice integer values, easy to use for our y outputs as well, which is nice. So that's kind of the goal today, is how do we pick nice integer values for the inputs that will also get us nice integer values for the outputs, so we don't have to deal with decimals and weird approximation answers. We can just get exact answers every time. That's the goal. Okay. So now, the first example today says let's go ahead and graph 1/4 of square root of x, and we're going to compare it to the original function, which was square root of x. So we start with 0, and I know if I get the square root of 0, it's 0, and 0 times 1/4 is 0. If I pick the number 1, the square root of 1 is 1, and then 1 times 1/4, so I'd get 1/4 times square root of 1, which is 1/4 times 1, which is 1/4. If I pick a 4, I'm going to get square root of 4 is 2, and that's going to give me 2/4, which is 1/2. If I pick a 9, I'm going to get 3/4 as my answer. And then if I pick a 16, I'm going to get 4/4 as my answer, which is 1. All right, and we'll see that there's some type of relationship every time I pick an answer here. All right, and how do our answers, when I'm multiplying by 1/4, how do those answers compare to just the square root of x answers that I had before? So I have 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, and those can be simplified to decimals if we wanted to. But how do they compare?
Do you just put the 4 under them?
Yeah, we're
Where's
just,
the denominator?
exactly, we're just putting the 4 under them. That's exactly right. We're basically dividing each of our outputs by 4. Or you could say, another way you could say it is we're multiplying each of them by 1/4, because that's exactly what we're doing. The outputs we had before, now we're just multiplying by 1/4. If I were to sketch a quick graph of this, I can go ahead and scale the x's. So let's just say, we'll go 4, 8, 12, 16. Not doing a great scale here. and then we'll say 1/4, 2/4, 3/4, 4/4, we can go ahead and plot our points. So 0, 0, 1, 1/4, 4, 1/2, 9, 3/4, and 16, 4/4. Looks something like that.
So basically, the graph of a radical is sort of kind of like a parabola to the side, right?
Yeah, it looks very much like a parabola, except it's turned sideways. But it's also only like half of that parabola. It's not the whole parabola. And that's because the radical limits what we can have for outputs, right? It changes our domain and range a little bit. When we talked about a quadratic function, the domain was always going to be from negative infinity to positive infinity. When we're talking about these radical functions here, like this one, the domain is limited. In this case, the domain can only be positive numbers again, so 0 to infinity. And it turns out the range can also be 0 to infinity here. All right, again, that's just because we can see the y values are going up this way from 0. But it's just going slower. It's going at 1/4 the rate that it was going on the parent function. And that's because we're just dividing all of our values by 1/4. That's the big difference here. Okay, that's how we would graph a quadratic function. And sometimes if we multiply by a number in front, that's what's going to happen. It's just the multiplier is going to stretch or shrink the function. In this case, we're stretching by a factor of 1/4, or we could say shrinking by a factor of 4. And yeah, the good question is it really infinity if it's slowing down on the y-axis? And the answer is yes, because what happens is even though it's going out to x, if I put in like $1 million for or $1 million for x, I'm still going to get an output for y. It's going to be a very big output. It's going to be 250,000 or whatever. But I can get whatever y value. It's just going to be growing slower on the y-axis. Okay, so that's the range would still be to infinity. Okay.
So one question.
Yes.
So wouldn't it technically be a parabola because you could do for the square roots it could be positive or negative. So could it?
No, so this is what's called a principal square root. It doesn't have the plus or minus in front of it, so it would not be a parabola. We'll talk about how you'd get parabolas when we get to a couple future lessons. We'll compare these two quadratic functions and how they look similar. But yeah, today we're just talking about just sketching the half of it. If it had a plus or minus in front of it like that, then we would have a sideways parabola. But we don't in this case. We're just asking for just the positive side. Okay? Okay, let's take a look at a cube root function now. So we'll zoom up real quick. It's a question on the first page. There we go. So we'll talk about cube root functions next. One thing I want you guys to see is if you want to, you can start filling in that table. But try and put -4 and do cube root of that in your calculator. And will it be undefined or are you going to get an answer? That's what I need you to look at. So work on the cube root table now. Get that filled out for us. Okay. And we're just going to round to the nearest hundredth. But I put it in my calculator and sure enough I get a negative answer. So the cube root does work with negative numbers. And I'll explain why that works in a second here. But go ahead and fill in your table first. So take a minute to fill in the table. So that'll work for both negative and positive infinity. There's one issue with the cubic function. It's the same thing where we end up with these decimal answers that we don't want. So we got to figure out how to get rid of those decimal answers. So again, what we can do is we see that in the middle numbers, we had a 0, a 1, and a -1. That gave us nice integer value outputs. So we want to figure out what other numbers we can do. So the best way to think about it is like, think about like if y was a -2, like we want a -2 as an output. We want to cube that number to get back to the input. We're doing the opposite of what we did to get to the input.
So -8.
Exactly, so it becomes -8. It becomes -2 times -2 is a +4 times a -2, and that becomes a -8. So we get a -8. That's going to be a nice input value we can put into our graph to get us a nice integer value for the output. And sure enough, if we tried f of -8 in our calculator, we would get -2. And that's why you end up with negative values at work, is because of when you're cubing, you're multiplying a negative by a negative to get you a positive. So it's like the negative by a negative gets you the positive, and then the positive times the negative gets you back to a negative here. Okay, that's why cube roots work with negative numbers. And that means if we did a +2, we'd get a +8 here. And then we can do the same thing with 3 and -3. So 3 times 3 times 3 is 27. So I can say -27 to +27 will get me the cube. That's the cube root of 3. All right, so cube root of 27 is 3, and the cube root of -27 is -3. All right, and I found those values by kind of going backwards from the y values, thinking about if I cube this y value, what's the x value going to be? All right, so kind of working backwards. That's going to be the theme for the second half of our lesson today. All right, we're going to look at one more example here. Let me get this to not be so blurry. There we go. So this one asks us, let's go ahead and graph y equals -2 cube root of x and state its domain and range. And we're going to compare this to the graph of y equals the cube root of x. So I'm going to use the same numbers I used before that we just found up above. We'll just say -27, -8, -1, 0, 1, 8, and 27. Because those will give us nice integer outputs when we cube root them. The first one, f of -27, is going to be -2 times
3.
the cube root of -27. So that's -2 times -3, which gives us +6. So that's what we'd put in there.
And then for -8, it would be so the cube root of -8 is -2. -2 times -2 is 4.
Exactly. So we get +4 for the second one.
And then -1, cube root of -1 is -1. -1 times -2 is 2.
Yep, you got it.
And then it's just 0, and then it's all reversed.
Yeah, so then we get 0, and then we go the opposite signs on the other side. -2, -4, -6. That's how we'd figure out these values here. Now I'm going to go ahead and sketch my graph. So we'll go ahead and sketch our graph here. Type in the x and y values. And then we'll put a scale on there. For the y's, just because we're going from 6 to -6, I think counting by ones is perfectly fine. We'll say 3, 6, down by 3, so there's -3, -6. And then for the x's, because I'm going all the way to -27, I know normally this would be 7 in each direction, so if I multiply 7 by 4, that would get me to 28 by the time I got out here. So I could count by 4s. 4, 8, 12, 16, 20, 24, and 28. So I'm going to count by 4s, so that way I can include all of my x values. So that's when I'm choosing my scale. I have to think about how to choose my scale so I can fit all those x and y values appropriately on my graph. So for example, I have negative 27, positive 6. Negative 27 is very close to negative 28, so I can put my dot right there. And then negative 8 and positive 4 is right there. Negative 1 and positive 2 right there. 0, 0, 1 and negative 2. 8 and 4, negative 4, and 27 and negative 6. And then I can sketch my graph through all those points and put arrows on it to show that it's going on forever. Because it's a cube root function, one of the nice things about cube root functions is hopefully we can identify the domain and range very quickly. Domain's going to work for any numbers. I can plug in negative numbers into a cube root. And the range will also be negative infinity to positive infinity. The big thing with this function is we're used to seeing the cube root on the left side be below the x-axis, and then it crosses at 0, 0, and then it goes above the x-axis. But because of the negative, it's reflecting the function. So that's when we talk about those transformations, which we talked about a lot in AGS2. The negative is causing a reflection, and then the 2 is stretching it by a factor of 2. Stretching it vertically by a factor of 2. All right, that's the idea for these problems. Okay. So now I've got 2 problems. I want you guys to try these 2 problems. One of them is a square root function. One of them is a cube root function. So problem 2, when I ask you to state the domain and range, hopefully problem 2 is pretty easy for you because it's a cube root function. So we know that the domain and range should be all real numbers.
So should we use the same numbers, negative 27, negative 8, and negative 1?
I would recommend that for the cube root function. Yeah, for your outputs, your inputs, you already know those are going to work to give you integer value outputs. Yes.
And then for the regular squared, we just use the 4, 9, 16, 25.
Yeah, exactly. For the square root function, I'd recommend using the 0, 1, 4, 9. Exactly. So those values there. All right. So go ahead and get started on the on these 2 problems now. Give you a couple minutes to graph them. And then I'd get not real answer there, and then wrong. And then nothing for y. The second one, 4 minus 3 gives me a 1. The square root of 1, thankfully, is just 1. And then over here I would have 1 plus 2 is 3. So my output would be 3. So that one actually works, which is nice. But then if I did 9, I would say, well, what's 9 minus 3 is 6. And then the square root of 6 is going to give me some weird decimal answer. So I'm really striking out here because I'm not getting a nice integer value that I want. And then I add 2 to that and I get 4.44. Actually, it would be 45. Sorry, it'd be 2.45 when I round to the nearest 100th. 4.45 here, and that's what I get for my y value. So unfortunately, just this method of going 1, 4, 9, 16, 25, 36, it's not always going to work. Because on this one I get 13. And I do the square root of 13, I get 3.61. And that gives me 5.61 there. 25 minus 3 is 22. And that gives me a 4.69, which would add up to 6.69 here. And that'd be my output. And then the last one, 36 minus 3 is 33. And that comes out to 5.74. 7.74 when you add 2 to it. But yeah, now I have all of these, like thankfully one of them worked, but I have all these other values that are not giving me nice, clean integer values for the outputs. So I have to choose something a little bit better that's going to work better for me. And the way it works is I know that in this case, oops, come on. Sorry, I went a little blurry there. We'll try and fix that. There we go. So in this case, I want to get like the square root of x minus 3. I want this to be 1, 2, 3, 4, 5, etc., etc., whatever. Or I guess technically it would be 1, 2, 3, 4, 5, 6. And in order to do that, I'd have to work backwards here. So I'd say, okay, like instead of square rooting to get to 1, I'd say what's 1 squared? That's 1. So, and this is 4, and this is 9, and this is 16, 25, 36. Basically, I'm saying I want x minus 3 to equal those perfect square values instead. So that way when I square root them, I get some nice integer outputs. That's kind of the goal here. So I'm kind of working backwards from the middle of this table. And to work backwards from the middle of this table, I'd say let's add 3 to all of the x values. So like 1 plus 3 is 4. 4 plus 3 is 7. 9 plus 3 is 12. 16 plus 3 is 19. 25 plus 3 is 28. 36 plus 3 is 39. And then going the other direction, I'm adding 2 to each of these values. So this would be 3, 5, 6, 7, 8, 9. And then my output values would be 3, 5, 6, 7, 8, and 9. I get nice, easy integer values to graph instead of these weird decimal answers in blue. So the trick for these types of problems is to kind of focus on the middle, this gray area that I highlighted in gray, and then kind of work backwards to figure out what's the x input I want to start with. It's going to be these really weird numbers, and what's the y output that I end up with to get some nice integer values. So if I took the x column on the left and the right column on the right, or the y column on the right, let me see if I can get this to not be blurry. There we go. We're going to go ahead and write down the table here. So we started with the x values of 4, 7, 12, 19, 28, and 39. Instead of the 1, 4, 9, 16, 25, 36, we start with these ones instead. And then we end up with 3, 5, 6, 7, 8, 9. That's kind of the y, that's where the y values would come from. So I'm just rewriting that exact same table that I had above, but I'm eliminating the middle rows now. I'm just writing what's on the far left and what's on the far right. And we get nice integer values in both cases. So if I were to sketch this one, I notice that I only have positive values for x and positive values for y. And then my x values are going all the way up to 39. So I know normally this would go to 14. So if I counted by 2's, I would get to 28 there. If I counted by 3's, that's probably going to be helpful. So we'll go 6, 12, 18, 24, 30. I'm only labeling every other one. That'll get me all the way to 42 there. But I'm counting by 3's on the x-axis. On the y-axis, I just need to go up to 9 so I can count by 1's. Okay, and I see that the first point is at 4 comma 3. So 4 comma 3. The second point at 7 comma 5. The next point's at 12 comma 6. 19 comma 7. 28 comma 8. And 39 comma 9. All right. There's just one thing I want to be careful of here. When I did this problem with my table up here, I'll let you guys sketch this real quick and then I'm going to go back up. My pages get blurry, so I have to be... So the domain for this problem equals 3 comma negative infinity. And the range for this problem starts at positive 2 and goes up. So it equals 2 to infinity. Now, if I were to switch screens here, I'll show you guys my other screen. We'll go to Desmos. Let me switch it over. On this, if we were to graph the parent function, I can click on this little calculator button on the bottom, or the little keyboard button there. Click on square root of x. There's the original function. And then do another one that's square root of x minus 3, and then get out of the radical and say plus 2. Graphing these two different equations. It turns out that those are the exact same equations, it's just that one of them starts at 3 comma 2 and the other one starts at 0 comma 0. So the last question that I was asking on this sheet here was, how does the translated graph compare with the other function? It compares that it's the same graph, it's just moved to the right 3 units, and then it's moved up 2 units. That's how it compares. All right, so we're going to switch back here. So we go to the right 3 units and then up 2 units. That's how this compares. So that's what I'm going to write down for my translation. So this graph moves right 3 units and up 2 units from the parent function. We've talked about transformations in AGS2. I know it's probably been a long time since you've seen them, but that's the idea with these particular problems. Identifying the domain and range of these radical functions, these square root functions, is probably the toughest domain and range because you have to think about both of them. But just think about where the starting point is and then which direction it's going. Is it going up and to the right? Is it going down and to the left? Is it going down and to the right? That's how you would determine your domain and range by looking at the shape of the graph. So I can see from this one it's going to the right, which is towards positive infinity on the x-axis. And then it's going up, which is towards positive infinity on the y-axis. Okay. Very last example today. We're going to look at a cube root function here. And this one's got a lot going on. It's going to have the... we're going to take this x value, we're going to add 4 to it. Then we're going to cube root it. And then we're going to multiply by 3 and add 1. To get to our output values. So I want to start here with just the cube root of the whole quantity. This is where I want to start with the values that I had before. Like, okay, I want negative 27, a negative 8, a negative 1, a 0, a 1. Actually, we'll do a little bit more in the center here. We'll skip the negative 27. We're going to go negative 8, negative 1, 0, 1, and 8. And the reason I'm choosing those numbers is because I know once I cube root them, hold on, I'm sorry, I'm doing that a little wrong. Those numbers will go here. My fault. And the reason is because once I cube root them, that's what this one is it's already cube rooted. They're going to be negative 2, negative 1, 0, 1, and 2 once they're cube rooted. So what I want to do then for these values is say, okay, well, I want those -2, -1, 0, 1, and 2 for my output, because then when I'm moving to the right, I'm going to multiply all of those numbers by 3. And then after I multiply them by 3, I'm going to add 1 to each of them. And then that would be my output values. And then going to the left, that's like, oh, I'm going to cube each of these values from the radical. And then after I cube then, I got to do what's the opposite of +4?
So it's -12 then.
I'm going to subtract 4 from each of them. Yeah, so it's going to be a -12, a -5, a -4, a -3, and a +4. That's how I would get my X and Y values. And then just to clean it up a little bit, I'll draw my table again down here and say, okay, my X value was -12, -5, -4, -3, and 4. And my Y values were -5, -2, 1, 4, and 7. Those 5 corresponding Y values to those X values. But I started at the radical and said, after I cube rooted, these are the numbers I want. So I need to work backwards, cube those numbers, and then subtract 4 from them. And then I'm going to work forwards, multiply by 3, add 1, and get my output values. Okay. Now I'll sketch my graph here. My X values going from -12 to +4. So if I count by 2's on the x-axis, I should be okay. -4, -8, -12, that would include my point. Going this way, get 4, 8, 12. And then the Y values are going up to 7, so if I count by 1's, I think we'll be okay. And then down to -4 and -7 in that direction. And now I can go ahead and plot my points. -12, comma, -5. -5, comma, -2. -4, -1. Or sorry, it's -4, +1. And then -3 and +4. And then 4, comma, 7. So this function is going to go through here, up pretty quickly, and then kind of curve back out. And we'll put arrows on it. The good news is it's a cube root function, so that's going to help me with the domain and range. I can plug in any negative number I want, and I'm going to get an output. So domain and range is going to be -infinity to +infinity for this one. Okay. Now again, how does this translate? What's being translated here from the parent function? Normally this function is centered around the point 0, comma 0, which is like I plugged in 0 for x and got 0 for y. But in this case, it's -4, comma 1. So essentially this is the center of it, the -4, comma 1 right there. So this function moved to the left 4 units and up 1 unit. Oh, just so you know, there's a little typo on my paper here. That should say +1, not -1. Because that's the equation we were working with, was +1, not -1 there. So this graph went to the left 4 units and then up 1 unit. That's what's going on here. Okay, it's always kind of the opposite of what you'd expect in the parentheses. It's that +4, so it's like going in a negative direction to the left. But then the other one, because it was a +1, That's outside the parentheses. That's exactly what's happening. It's going up 1 unit. And the last part here just asks, how can we use the graph to solve the graph of -5? So if I were just thinking of the line y equals -5, I just look for the point of intersection, which actually happens to be on our graph as well. Oops. When y equals -5, x equals -12. Okay. One way you could solve that really quickly is you could go onto Desmos and graph the line y equals -5, and then you can graph the line 3 times the cube root of x plus 4 plus 1. And let me show you how to let me show you how to do this on Desmos really quickly too. I'm sorry, did you have a question? Yeah.
X equals -2
For which one?
for -5.
Well,
Oh wait, never mind. Sorry, that's my bad.
Sorry, yeah. So when you look at this on Desmos, I want you to see that there's no cube root function here. So what we'll have to do is we'll have to do one equation that's just y equals -5. And then we're going to do the other one that is 3. And then we're going to do parentheses x plus 4. And close the parentheses. And I'm going to raise that to the 1/3 power. And that's the same as a cube root. And then I'm going to say plus 1. And I'll be able to graph the other line. And then because of my viewing window, I'm going to set this to the same viewing window that I put on my piece of paper, which is the x-axis is counting by 2s from -14 to +14. And then the y-axis, we were counting from -7 to +7. And we're counting by 1s on the y. So that's kind of what our graph looked like. And there's an intersection at -12, -5. That verifies that we had the correct answer when y equals -5. We got the right answer for our graph. And then we see this weird point at 0, which makes sense. We didn't have a good point for 0. But if we get to like y equals 4, we can see there's a -3, +4, which was on our graph. We also know if y equals -5, or sorry, if y equals, if we could type in x equals 2, x equals -5, we could see the intersection at -5, -2, so it's showing all the points that we wanted. It's showing the correct points on our Desmos graph, which is good. But we're finding those integer values from our graph. I'm going to go back to the other screen now. So let's see, back to the iPad. All right, so good question here. It asks, where did I get these values that we started with? That's a really good question. So these values right here. And it's just because typically when I do a graph, I want to choose really easy numbers. So I think the easiest 5 numbers are going to be that range from -2 to +2, the smallest possible numbers. That's kind of how I chose those ones. I also chose them because looking at the gray, I wanted to look at nice, easy cube root numbers. So going from -8 to 8 and cube rooting all of those numbers, it's going to get me these values over here to the right of it. So that's kind of how I chose those ones for that. If I were doing a square root function, the numbers I would have wanted to choose were probably 0, 1, 4, 9, and 16 on this left side. And that would have given me 0, 1, 2, 3, and 4 over here. So that's why I was choosing those specific numbers. All right, that's where those numbers came from.